Okay, so for part A of FRQ 3, I draw a free body diagram. So this is our block M, and there will be multiple forces acting on it. First will be an Fk, due to the fact that there's a mu k existing. Next is the applied force F, and then we have Fn, which will be trying to pull it. Will be working against Fg, Fg will be pulling it down. And now we have free body diagram right here. Next up for part B. So to find acceleration, what you would do is you would derive it from displacement formula. So we could say, in this case, it will be equal to change in x is equal to VI t plus 1/2 AT squared. So we know our VI is going to be 0. And then so if it's 0, this will cancel out and we'll be left with 1/2 AT squared. So then what we do next is I say for A, so we times 2 on both sides, divided by t squared is equal to A. We can break this up to make 2 delta x over t times 1 over t is equal to A. And with this, we will say our vertical axis will be 2 delta x over t, and our horizontal will just be t. And then we could fill it in right here. So I'm going to represent this as A for acceleration, and unit will be meters per second squared. And if you plug all this in, you should get about 1.8 for all of these values, because I'm comparing it from the change in time from 0 to this, and it starts and the initial position is 0. So it will be 1.8. So this horizontal axis will be in time for seconds, and this vertical axis will be 2 delta x over t, which the unit here is meters per second. And then I'll scale this bottom one by 0.3 seconds each. So 0.3, 0.6, 0.9, 1.2, and 1.5. I'll scale this vertical by 0.5, so 0.5, 1, 1.5, 2, and if I in 2.5. So then we can start looking at this. So at 0.036, my first 2 delta x over t is going to be 0.36. So 0.136 is about here, so it'll be right around here. Then at 0.234, right here. At 0.234, my delta at 2 delta x over t is 0.91. Then 0.493, it's going to be about 1.33. And then 0.729, it will be about 1.62. So 1.62 is about here. And then next it's at 1.521. It will be at, which is a massive jump, about here. It will be at 2.34. So it will be about here. And then if we try graphing this, it will come out as a straight line-ish, about. And then because of the way it's shifted and stuff, it's gonna be, the scaling might be a bit off. And then we could look at the experimental value for the A. In this case, what we found earlier is so I do right here, 3D. So it's 2 delta x over t squared is equal to A. But then we look at the slope here, it changed by 1.521 times 1.521. Oops, this should be the time, not the displacement. No, this is displacement, my bad. 1.521 over 1.3 squared, which is the time. And in this case, for A, so we do this, the answer will come out to about 1.8, which is meters per second squared. In in this case it will be in the direction, it will be in this direction so far. And this will be my A. Using that slope right here, for E, we're gonna derive for the coefficient of friction. So we say net force is equal to MA. And the forces in this case, we're gonna be looking at the horizontal. So we're gonna say, so the F applied horizontally minus the force of friction is equal to M times A. So our horizontal force is gonna be F cosine theta, and I'm gonna move this MA to this side, is equal to FK. Now we're gonna expand FK out. So I'm gonna rewrite this minus MA. So FK is Fn mu K. And then now we're gonna try to find Fn. So we know the net force in the vertical direction is equal to Fn minus Fg minus, in this case of the problem, the applied force is going down, so Fy. And this will be equal to 0. So then we can say F plus Fg plus Fy is equal to Fn. And we know M, in this case, Fg is Mg, and Fy is going to be F sine of theta. That will be our Fn. Now I could replug this back in, so I'm going to move this over, divided by Fn for back over here. So you have F cos theta minus mass times acceleration all over Fn is equal to mu K. And then what we can do after is substitute Fn. So F cos theta minus Ma over Mg plus F sine theta is our equation for mu K. And for the force of kinetic friction, so we 3F, this will just be net force, which is equal to X, and which is equal to Ma, which is equal to Fx minus Fk. So then we can isolate for Fk here. So we subtract, so say Ma minus Fx equal to negative Fk. And then after that, we're going to say, we're going to move the negative sign over here. So we're going to say multiply by -1 on both sides. You get Fx minus Ma is equal to Fk. And our Fx we know is F cos theta minus Ma is equal to Fk. So now I'm going to substitute an F in all my variables. So F is 12 newtons times cosine of 60, which is given, minus the mass of 2, which is going to be equal to 2A is equal to Fk. And so, since we know our acceleration is going to be 1.8, 12 cosine 60 minus 2 times 1.8 is equal to Fk. My Fk will, as a result, equal to 2.4 newtons. And this will be working, and if we're going to put in a minus sign, the minus sign will be working against the line of motion in this scenario, which is going to the right. Okay, so for the next part, we're going to finding the mu K. So we know from past, the mu K is equal to, as we saw earlier, F cosine theta, up here, F cosine theta minus Ma over Mg plus F sine of theta. Then we just plug it in. So F is 12, theta is 60, minus the mass is 2 kilograms times 1.8, which is our acceleration. The mass is 2 times 9.8, which is the force of gravity, plus 12 sine 60. And this will come out to 0.08, and that will be our mu K. And we know that for that we could use mu K. I only use this formula we got earlier. Ma over mg plus f sine theta. Now, I'm going to isolate for a to test it out. So we multiply by mg plus f sine theta, so we get mu k times mg plus f sine theta is equal to f cosine theta minus ma, and I subtract, so it's mu k times mg plus f sine theta, and I'm also going, after that, I'm going to be dividing it by negative m, so then I'll have mu k times mg plus f sine theta minus f cos theta is equal to a over negative m. And now we can look at the function here. So theta, so mu, mg, and f will be all the same in this system. But we look at theta now. So we look at theta now, right? So we see f cosine theta will be this, I'll distribute a negative. So it's f cos theta minus mu k times mg plus f sine theta over m is equal to a. So our f, our mu, mg will be all the same in the system, even if we change the angles, because that's the given. But then as the angle decreases, what happens is theta here, it'll decrease, but cosine gets bigger as theta approaches 0. So when it decreases, this value here will get bigger. But in contrast, here, sine theta, as theta decreases, sine decreases. So then this value will get smaller here, and which will be added to this value. And because we're subtracting by a smaller value, and our other value is getting bigger, therefore, as theta decreases, the acceleration of the block increases. Okay, and then for the next part, we're going to be graphing a of t. I'm going to check this out first. So a of t, so I'm going to put this axis right here as a, which is meters per second squared. This here will just be t. And then, which is in units, is seconds. So then, what I'm going to do next is I'm going to graph a of t. So let's say this is 2.5, 2, 1.5, 1, 0.5. My a of t will be about here. And a in this scenario is going to be always going to be 1.8. So it's going to be a straight line all the way to 5. Next up, we have v of v, which is meters per second. Then here is time again, which is seconds. And then now I'm going to be graphing this. So what we're going to notice is since this is just a straight line, horizontal line, this will just be increasing at a constant, the velocity will be increasing constant rate at about 1.8, which we say is this. Let's say this slope here is just 1.8. And this will be our sketch of the velocity time graph. And now for the final one, the position time graph, I'm going to label the horizontal as seconds again, t. And then here is x in the form of m. And then now, this is a linear function, linear with a slope. So now this x, a t, would just be, instead of being linear, it will be a quadratic. And as we notice from here, so from above, this is a positive acceleration, so we know our graph is going to be concave up, and this one is increasing, as we can see here, because it's positive. It's always positive, so that means this will be a positive concave up function for x of t. So I could draw that as a parabola, and we're saying x at the initial, it's going to be 0, so it's going to be it's increasing over time at a quadratic rate. That's a quadratic. And this may not be as accurate, but the scale might be off, but this is what would look like, because it will be a quadratic if we integrate this x of t